welcome to good afternoon to everybody who has already joined the Sano computational medicine seminar. Well, we still have to give some 2-3 minutes to all people who are in the queue waiting to join us. And in these 2-3 minutes, we will start the seminar. It will be the last seminar before Easter, and then we will have no seminar on the 2nd April because it is holiday in Poland. And on the 1st April, sorry. And then we hope we will have the next one on 8th April. So, well, let's have a look how many people we have already. Well, at that moment, we have already 20 people, 20 participants of the seminar. So I think that it is probably the typical number of participants. So, well, welcome once again to our seminar. And well, today as a speaker, we have Amanuel Ergogo from Health Informatics team led by Przemek Korzeniowski. Amanuel is a PhD student in this team led by Przemek Korzeniowski, and Amanuel has a very interesting way to research in his area, because first he obtained Bachelor of Science in Electrical and Computer Engineering in Ethiopia. He spent some time working as an assistant lecturer at this university, and then he moved to Poland, to Wrocław, where he got his Master of Science engineer degree in Control Engineering from Wrocław University of Science and Technology. And then he moved to Krakow to Sano, and he works in the field related to robotics in medicine. And Amanuel will give this talk today about progress of his PhD research. And well, if you have any question during his talk, please just put this on questions and answers or in chat. And but anyhow, after the talk, there will be. So, Amanuel, the screen is yours. Please go on.
Hello, good afternoon, everyone. I hope you can hear me. And thank you, Mariam, for the introduction, and thank you all for joining this seminar or session. I'm happy to share you that my PhD project is called Assistive Robotic Caregiving, or in short, ARCare, which is collaborated with Dr. Diago from University of Verona and Dr. Natalia here from Sano, and lately promoted by Professor Teresa from Warsaw University of Technology. Sorry. In this presentation, first we'll see the need, challenge, and opportunities in assistive robotic caregiving, and what types of caregiving tasks ARCare is considering. Next, I'll present you what planning or decision-making methodologies we use to develop robotic caregiving systems. And following that, I'll tell you about what we have achieved so far. This looks the outline of this presentation. Challenge in healthcare, such as aging population, rising healthcare costs, shortage of healthcare workers, people with disabilities, caregivers, prolonged stress and physical demand, and the desire of or people need to live independently have promoted or pushed the healthcare industry and individuals to seek assistance from intelligent machines. As you see here, okay, this slide, in recent years, there has been a growing application of assistive robots, despite challenge related to ethics, trust, and acceptance of such systems. This is particularly evident in caregiving scenarios or caregiving robots, where issues arise due to their human-centric natures, because they work and interact in human environment. The figure at the right top shows Moxie robot from Diligent Robotics, deployed over many hospitals in the US. And it helps nursing staff with non-patient centered tasks, such as running patient supplies, delivering medications, and other related tasks, so that the nursing staff can focus on patient-centered tasks. In addition to this, there are various applications ranging from physically assisting robots to assist patients with disability and elderly with daily living tasks, to robots for social and cognitive assistance for people with dementia, and robots for companions, including robots in diagnostics, medical imaging and acquisition, rehabilitation, and radiotherapy applications. As you see here at the right bottom of the slide, it's a zipline drones, which was implemented, I think, 7 years ago in Rwanda. And yeah, it has been delivering some platelets, and some necessary materials to remote hospitals. And it has been used for, maybe you have heard this news. Beside all this, all the needs and application, we have seen current robotic assistive methods exhibit limitations in efficiency, particularly in applications involving human and robots, highlighting the need for improvements. Unlike the industrial robots, which operates in structured and less dynamic environments, in assistive caregiving, robots must possess advanced skills to understand human and interact effectively with both human and the environment. In this slide, we see 3 spaces that the robot can operate. In the earlier times, the term robot is used for a giant mechanical structures that performs 3D jobs, which are dirty, dull, and some demanding jobs. And I even found the word robot is derived from some Slavic word robota, that means forced labor or something like that, as shown in the slide here. Okay, maybe I have to put the pointer, laser pointer. Okay, can you see my laser pointer?
Yes.
Yes, okay, thank you. In this environment, in the industrial environment, robots are less intelligent in understanding their environment, and they functions in structured and less dynamic and isolated environment. They need to be fenced and kept away from human. And they need building some predetermined or predefined static environment, maybe with some installed sensors, markers, and other infrastructures. Unlike some of the technologies we are seeing, so like self-driving or autonomous cars, we see in roads and infrastructures that are built for human. At all, these robots need their own environment and then cannot be operational or functional in alongside humans. That is industrial environment robots. In human space, the second space, robots are expected to perform tasks in human-centered environments with more or less physical interaction with human. And the robot must be intelligent enough in understanding their environment and functioning and dynamic, and that means changing world and human environment. Example for this can be some assistive robots, service robots. I don't know, some of you have encountered or met some robots in some shops, I don't know, some service robots. Example of this can be again a Moxie from Diligent Robotics. And here we see also a cobot from our lab, is a factory robotic arm in our lab. It's designed to operate in human space. Furthermore, we see in a third space or personal space, we see robots in personal space, which are intelligent in social interactions with human or pet-like embodiments mostly. And some studies shows that this this kind of robots in personal space gain much acceptance compared to other robots. And yeah, what we are doing then, so the topic ARCare deals with assistive caregiving robots to operate in human space. This is a second space in here. So what applications and tasks, caregiving tasks ARCare considers will be the next question. Caregiving tasks refer to activities involved in providing care and support to individuals with physical demand from the perspective of this project. And this topic mainly focus on elderly and bedridden individuals who may have limitations in performing activities independently. Assistance with activities of daily living, such as feeding, as you see in here, such as feeding. It's assistive feeding robots called OB robots, which is commercially available in the US now. And handover objects are mainly caregiving tasks we consider here. As you see here, robot human handover or robot passing some objects for person in need. Handover is a scenario where robots grasp and pass various objects for a person in need. And this involves planning, planning or decision making on how the robot grasps various objects, plan safe trajectory to approach user hand and make decision on whether to release to human hand or not. Robot assisted feeding involves planning or decision making on securely skipping various foods without dropping them and safely delivering the food to the user's mouth. So what are our research questions, and then how we can achieve this thing? Mainly use methodologies in here. Here one of the approaches using classical planning methods such as A star or random trees to find some plan or solution in a space, in a Cartesian space that takes robots in the vector from some desired position to some initial position to the desired position. And this classical planning approach use traditional AI planning technique used to determine a sequence of actions that the robot should take to achieve its goal. And here we can see as example, picking a mag from a middle rack without collisions, without any collision. And it maps the environment as an evenly spaced, as we see here, grid environment as evenly spaced field of binary random variables, each grids representing the presence of obstacle. For example, these black ones, there's presence in obstacle. Obstacle at that location and environment. So how these maps can be made from map posterior formula here, where this one is the posterior probability of the cell being occupied, given the sensor observation and the in the vector state or position pulse of the robot can be computed as the product of likelihood of observing sensor measurement Z, given the cell is occupied and the robot pose is at X, or state of the pose of the robot is at X, times this is called prior probability of the cell being occupied, given the state of the X, divided by the total probability of observing the sensor measurement Z, given the state X. Using this, we can calculate the map of this environment that's just simply represented in 2D grid. And having this map, classical planning algorithms such as A star or RRT, as you see in here, can plan a path from some starting position, initial position, to desired goal without colliding with these obstacles mapped environment. In a mapped environment, they can actually plan the optimal path to that takes the robots in the vector from initial to desired position. Yes, this approach is great to plan a path which takes robots in the vector from point to point in a Cartesian space without colliding with some obstacles, but not suitable for contact-rich tasks where the robot has to make and break appropriate contact with objects to manipulate object states, such as position of the object or shape or other states of the object. In addition to that, computational cost in high-dimensional state space, real-time constraints, and uncertainty in dynamic environment limits the usage of these classical methods. So also the other widely studied method here is deep RL or deep reinforcement learning. It allows robot to learn behaviors or policies through trial and error rather than relying on explicit programming or some planning algorithm as we discussed. The robot receives feedback from the environment in a form of rewards or penalties based on its action, and it adjusts behavior accordingly to maximize cumulative reward over the time. Reinforcement learning is suited for problems where the environment is uncertain or whether it's difficult to explicitly model or map all the aspects of the problem. It's more suitable to learn or to approach the problem like end to end without modeling or knowing it. It's easy to plan functional motions, but hard to plan natural and acceptable motions using this kind of approach, because there's a limited way to define the behavior of the robot. It's just only reward function, and it's hard to define, and it's limited to shape the behavior of such actions. So it can be functional, but it's hard to shape the behavior of the robot as natural and an acceptable motion. I think this is a P on there. I'm gonna skip this one. Now we see robotic voice, maybe robotic voice is a history, and that means nowadays we do have like more natural voices from computers, and in real time we know that robotic voice, can we achieve something like that in robotic motions to something natural and acceptable thing? That's the thing. And this is the robot developed by Disney Imaginers. Imaginers is a term for creative engineering, which comes from imagination and engineering thing. And they're so talented in giving some personality or for characters, robots, and it's not definitely programmed this thing. I can maybe play this one. It's hard to program or do the other way these kind of motions. It's super smooth and so natural, acceptable. Yeah, this behavior of the robot drives a lot of discussion among robotics researchers. And so in here also we can see a video from our lab to scope some kind of serials. You can see maybe the smoothness of these motions, I don't know. So, okay, can we achieve some kind of acceptable and smooth behavior of the robots? And this takes us to imitation learning, where a robot learns to imitate human behavior instead of being programmed or learn some weird, strange, or random functional behaviors guided by reward function. Reward. Imitation learning involves learning a policy by observing human demonstrations. instead of exploring the environment through trial and error, like in reinforcement learning, imitation learning leverages existing expert knowledge to directly mimic experts or human behavior. Imitation learning can be particularly useful when it's difficult or time-consuming to manually engineer reward function. It's actually hard to shape these functions, or when the task involves complex behaviors that are hard to capture. So explicit reward signals. Imitation learning, despite its promises, there are it faces some challenges, including its need for high quality of demonstrations and distribution mismatch is called, since the states are not states of the either the states of the environment or the robots are not deterministic, and it derives continuously, and as you see in here, it derives continuously, and it caused the learned agent policy to perform poorly on unseen states, since the state of the robots or environment derives, since they are not deterministic. So in here, this is the desired trajectory for this 2D simplified 2D object to follow. But and here we see the learned policies drifting because of this distribution shift, as I mentioned, because of the non-deterministic nature of the states, either robots or the environment. So in this time, there is no data how to recover this learned policy to follow or track the expert desired trajectory. This is one of the challenges in imitation learning. And actually the first challenge is also a need for high quality of demonstrations to capture yeah, human interaction with the objects or robots. Yeah, just to recall the problem with the imitation learning, it needs high quality of demonstration and agent failure due to distribution shifts. Those are the problems in imitation learning. In this paper, in this work, which was presented at the IEEE VR 2024 conference, we achieved to keep human in the loop of imitation learning process to correct and provide data for the agent to recover in this case. So our work, Hello Tail, is a virtual reality framework for interacting, collaborating, and teaching robots in digital and real environments. And it allows learning sequential decision making from human expert demonstrations while offering intuitive while offering human intervention capabilities during the autonomous execution of the robots, along with intuitive 3D interface, as you see here, intuitive 3D interface and action feedback for the user. So the system was composed of mainly three components. The first one is VR-based robot interface. It enables human expert interaction with the physical environment through VR. It allows pass-through mode and teleoperation mode. That means in teleoperation mode, human can be somewhere else far away from the robot or from the physical space or from the robot, and has the feedback and interface using the digital twin or virtual environment, digital twin of the physical environment or virtual environment. In pass-through, the human expert, human can be alongside the robot or physical space and can control or interact with the environment using the default cameras from the virtual reality headsets. The digital twin is a virtual model of the physical environment, and it provides training data for the learning agent and supervision feedback for the human. And the main part of this work was task execution and learning. It learned the task execution policy from a human expert by aggregating interaction data, and it allows the trained agents to operate autonomously or in a collaborative mode. So to test this system, we've set up an experimental setup. We set up an experiment, and we consider a task of moving a white bottle from peak position to move white bottle from the peak position here to and place in the place position in less than 60 seconds while avoiding these distractors, collision with distractors. And the experimental setup, it consists the arm robot, 7 degree of freedom factory X arm robot, a robotic manipulator with 2 finger gripper, and Oculus Quest headset, Oculus Quest 2 headset, DIPS camera, and DIPS camera or 3D camera, and the workstation PC. We consider, as I said, the representative task of moving this bottle from here to here within 60 seconds without colliding with the distractors. So the human operator controlled the robot via Oculus Quest in teleoperation and pass-through modes. As the operator execute the task, the imitation learning agent collected data for task execution policy learning. We access Hill Hotel across 4 scenarios, evaluating task completion time, success rate, and hands-free time. Example, the time the human operator spent in supervision state, we call it hands-free supervision time. Task completion time measures how long it takes for either human operator or autonomous robot to complete the light blue pass in here. It's ideal pick and place pass, starting from initial position, peak position, place position, back to initial position. And success rate is a percentage of successful task among trials, defined by accurate picking of from the radius, red radius in here, the left, and precise placing within the radius red circle in place position. And all this accomplished in less than 60 seconds. If not, that means the task is failed. So in the first 2 scenarios, human pass-through and human teleoperation, the user performs the task using teleoperation and pass-through mode, as I described previously. And in a third scenario, the robot autonomously executes the task without human intervention, termed as we call it pure agent. And in the last scenario, the robot's execution is supervised by human operator, allowing interventions when necessary, such as in the event of failed grasp or failed robot execution, and we call this high-low tail. human in the loop. For each scenarios, the user performed 15 trials. We evaluated this framework in terms of two things, that is interaction and human-robot collaboration. In terms of interaction, pass-through, reduce pass-through. In terms of human-robot, in terms of interaction, pass-through mode, the first one, reduces the task completion time by 19 point something percent, despite 16% decrease in success rate. This is due to the communication overload in the second one. In the second scenario, until operation, there's some kind of communication overload because it operates from remote. And in human pass-through, the real-time rendering lag was the problem, and it caused some kind of, as we see here, reducing in success rate. In terms of human-robot collaboration, Hilo-Tail, our method, had the highest success rate together with human teleoperation, that is 19 point something percent. But with higher hands-free time, as you see in here, because most of the time, 71% of the time, the user is in supervision state, not actually doing the tasks, because the pure agent is helping the human. When the pure agent fails, the human is also collaborating with this one. That increased the success rate, and while giving some hands-free time or supervision time for the human. So in conclusion, we present virtual reality-based framework for interacting, collaborating, and teaching robots in digital and real environments. Our system provides an intuitive 3D action and feedback interface while offering, as we have seen, human intervention capabilities to correct and collaborate with the agent. And our system improve the task success rates, maintaining human level completion time, and provides extensive hands-free supervision time. And that means it facilitates human-robot collaboration. We aim to expand experimental validation by extended user test with more users, and also including some previously mentioned caregiving tasks. So I have time? If I can have the time, I can continue, or maybe that's enough.
Well, I don't. Do you like to have more time for? You have more time, of course. What do you like to do now? If it is just getting questions, so this is the time when we will do it. So not a problem.
Okay.
Okay. Then mention about some video. So it's no.
Then I think I'm done. I'm finished. And yeah, thank you for listening. If you have any questions or some suggestions, comments, you are welcome.
Well, so Amanuel, many thanks for your talk. Now we are in the time of discussion. Well, first of all, before we will ask for asking questions, participants of the seminar, maybe it would be great if I could invite the team leader, Przemysław Korzeniowski, to to explain something more about how the research which are done, performed by Amanuel are somehow linked with the overall research agenda of your team. Femku, if you would be so good and
Hi, can you hear me? Can you see me?
Yes, we can hear you.
Excellent. So our team, Healthcare Informatics, is looking basically at improving patient care by technology, which is very wide. The main focus is but you all know robotics and collaborative robots domain is currently booming, and I guess this is especially valid in topic for Poland. So, for example, in the context of surgical robotics, which this project is not about surgical robotics, but there is also like similar problems may occur with other medical stuff. So the average age of surgeon in this country at this moment is 59.5. Okay, so and so in a couple of years, like most of the people will be retired, and the problem is that young clinicians, young students, medical students are not really interested in surgery because it's a very difficult procedure, difficult medical specialty with a lot of responsibility. With a lot of stress, so they prefer other specialties. I think that from what I checked last time, like more than half of the places are not fulfilled, residency places. So long story short, basically Poland will experience like a terrible lack of medical staff at all levels, starting from surgeons, but also probably nurses and so on. So we can't fill it with simply with immigration from various reasons. I don't want to get into this. So I guess the way to go is probably, and I think it's also like a great combination when these days, especially with, for example, large language models, when this collaborative robots will not only be like, passing objects and helping with basic hygiene, maybe help you to dress or move things around, clean up kitchen, but they will also be like able to communicate in natural language with your devices, and this is coming like really. So long story short, I believe that this kind of projects really fit into agenda of healthcare informatics team. Actually, it was one of the first projects. It was called initially a remote examination room. So the idea was to have this collaborative arm to examine patients, both like fully autonomously, but also via teleoperation. And it slowly evolved when Amanuel joined also that one of the sort of spin-offs or branch of this project could be to assist mobility in patients. So, yes.
Well, many thanks for this explanation. Well, on the first on the title slide of this presentation, there was also name of Natalia. Amanuel, it would be good to know what was the contribution of Natalia to this, because Natalia is to some an expert in let's say interaction with humans. So could you please give some information about your collaboration with Natalia? What you have achieved in this collaboration?
Okay, well, thank you. Maybe I'm gonna go to. Okay.
Yeah, unfortunately, Natalia is not here.
She's not there. Okay, so I'm good. The question is actually for me, so I'm gonna answer. So yeah, in short, we haven't done like much of the collaboration at this stage because first we have to yeah, mostly this time this project like at the stage of the making the ability of robot to interact with the environment, not with human actually at this stage. So as I have discussed, most of the tasks are like dealing with the interaction with the environment, not human at this stage. So when the next stage comes, like to help or to assist human, we have to understand human. We should be like, I mean, the robots should understand human. The robots should be accepted by the human, trusted by the human. So that's why I was also discussing this position and these spaces like personal space and things about acceptance, trust, and all those things. So since she is expert in this field, she can be valuable like to collaborate with this project. Thank you.
Well, many thanks for this. And well, as I understand, because in this presentation we mostly seen the results of your work, in the sense that we have seen moving robot. Maybe you could explain more about, let's say, your contribution from the point of view of, let's say, some theoretical and, let's say, programming contribution to this topic.
Okay, could you repeat which robot you said, which slide maybe?
Well, no, what I'm asking about, because you presented the results in the form of robots moving or going on, and I think that behind of this there is a kind of work in let's say finding best possible algorithm programming. So could you give some comments on this type of work?
Yes. So yeah, in this work, basically, my contribution with the rest of authors is yeah, I was able to develop a framework, intuitive framework, as I've shown. This was the main challenge to capture high quality of demonstrations. So using virtual reality, I was able to develop this virtual reality based framework for the user or for a human to intuitively interact and show the robot or yeah, in short, to interact with the robot. And on top of that, the other thing is I was also able to add some machine learning models in that to capture these interactions with the environment, human interactions with the environment while the human is doing things or executing some task, as we have discussed. The method that's called task execution and learning method. This method can learn these interactions. Those are one of the contributions. Yep. Thank you.
Thank you. And if you compare the, let's say, the approaches which are used in the models which in robots you have presented in the beginning of your talk, with coming from outside and what is novelty in your approach? What is new with your proposal?
I couldn't grasp which robot are you talking. Are you talking about this slide maybe? Sorry.
Yes. So what is novelty of your research in comparison to this nice lady?
Okay, in this slide, what I was trying to say is I was trying to introduce imitation learning. That's not anything novelty, but we have some task on progress, as we see in here, acquisition policy for robot assisted feeding. That is what we are doing. That's something on progress. That means for robots to be able to let's say accuse different kind of foods, various kinds of food types, to help patient in need, like to assist with feeding actually. So in this one we are trying to achieve some kind of natural and acceptable motion using the imitation learning from human. So this is still ongoing thing. Yeah.
Okay. Well, now we have a question from Wiesław. Wiesław, it's great that you are here. Could you please ask the question and take part in this discussion?
Okay, thank you very much. Can you hear me?
Yes.
Oh, fantastic. First, I'm happy seeing the names on the first page. I have seen my old friend, Professor Teresa. I'm not quite sure if she is online. If she is, I'm saying hello. Yeah. Okay. Regarding this work, I think it's a very nice topic. It's a very important topic. I would say that probably state of the art shall be a little bit extended, because we know that there are several robots in surgery performing different tasks, like Neuromate, probably the first robot in neurosurgery, which has been used mostly as a positioning device, or another popular robot, Da Vinci, for scaling motions or transferring motions. So I think it's good to extend the state of the art. Of course, from point of view of avoiding of obstacles, we know that there are robotic games, playing soccer and so on. So I think it's also a good idea to look at this kind of applications, because the issue is not only the avoiding of obstacle, but the issue is, of course, to do it very, very fast, without mentioning robots which are used for cleaning, which really are wonderful in avoiding obstacles. In fact, my main questions already were asked by Marianne. So I was also interested what is really new in this kind of work, since this is a PhD work. I understand that your main application is, for example, feeding. In such a case, do you consider safety? Because I think if a robot is supposed to feed a patient, safety is a key issue. Is it in your equation when you consider your research?
Okay, thank you. Thank you for the comments and the question. Okay, let me start from the comment actually, because the question is also based from that. In comments regarding the state of the art, the surgical robots and all the other robotic application you mentioned, they are not actually doing by themselves. They are just device operated by human actually. That means they are not autonomous in short. So when we come to automation, the state of the art is still like underdeveloped, like just it's hard even to pick unknown object, some kind of unknown object without doing some, I don't know, modeling object or things. So it's still, yeah, it's still in growing stage when it comes to automation. Regarding your question, mostly I'm considering the automation part, or robots doing things autonomously without human, actually, without needing human aid, but they learn from human. So what we are developing is on top of those state-of-the-art, maybe used, that is teleoperation used in those surgical robots and things. We are adding some machine learning models to learn from those interactions. That was what I was presenting. And in terms of the safety, yes, it's actually the robot things related, research related with the robotics. It's actually kind of huge, and in short, I'm not considering safety because it's a huge field in itself, and there's a lot of researchers working on safe autonomy and things. So I'm not really considering on safe autonomy, except some simple safety things like, I don't know, some switches and things, but I'm not really doing the research on safety autonomous or safe autonomous planning or things. Yeah, thank you.
Okay, thank you and good luck to your work.
Many thanks, Wiesław, for being with us. Many thanks, and for discussion. Well, I'm looking for more questions. I see that there are no more questions. So, well, as there are no more questions, I would like to thank very much Amanuel for this talk. Many thanks. I would also thank Wiesław and Przemek for contribution to the discussion today. Well, many thanks to all 32 participants of this seminar. Well, and because we will meet after Easter, so it is just almost five days before Easter, but anyhow, all the best wishes, best Easter wishes for all of you. And well, it would be great to see you once again in 2 weeks from now on Monday, April 8th. Many thanks and goodbye.
Thank you. Happy